The best way to score well on the finals is to just continue to keep up with the packets and continue to work on them, and gradually they get easier and easier and easier to where you're ready to go. So that's the goal. So I would say let's take questions on the multiple choice. We pretty much had went through the first part of the multiple choice, but if you have some questions back on the first 28, that's okay too. If you want to do that, we can do that. But then let's get into the calculator section a little bit here today. And we are going to spend a fair amount of time today doing this. And I want to talk about the free response ones also. So what's that, Allie? 19. Okay, because this is, hopefully when we get into our last packet or two before the finals, we're a little more independent on some of these, especially some of the older problems. In this one, I probably tend to help you a little more and spend more time working on some of them than we might later on. But okay, let f be this function, differentiable. These are the f and f prime values. The line tangent to f and parallel to the segment between the endpoints. Boy, that's a lot of stuff going on there. Let's break it down. What's parallel mean? Segment between the endpoints means I'd be looking at these points right here. So I would want to do that slope. So 26 minus 2 and negative 2 minus 10. So that would be negative 2. So that means we're interested in this line because of that right there. So we need our slope to be negative 2. What's it want to know? Oh, where it crosses the y-axis. So in other words, write the equation of the tangent line. So we get y equals x minus 4 plus 23. And so then it would just, and a slope out in front. There we go. So it'd be negative 2x plus 8 plus 23, which would be negative 2x plus 31. So there's our y-intercept, which is what they want. So there would be right there. Okay? 42. 42 is a good one. Now, it's possible, I haven't looked at this one enough to know, but it's possible that a person could maybe figure out some things with circles and rectangles and geometry to maybe figure this out without any calculus. Possibly. Because that does happen sometimes in the multiple choice. The free response, of course, it doesn't matter. You can't do that. You're getting credit. You're getting credit, the free response, for showing the calculus steps you need to do it. But in the multiple choice, it doesn't matter. The multiple choice, you just got to get an answer. But just to review, I'm going to go through how we learned this. So what is the max area? What we said is to do a maximum, you have to write an equation of what it is that you're trying to maximize. Well, we're trying to do the area of a rectangle. Now, they said you've got a semicircle radius 8. Well, the best way to do that is to put it on an xy axis and give it an equation. So this would be the part many of you probably got stuck at and then just didn't know where to go from there because you didn't have an equation. What you want to do is, and hopefully we all remember the equation of a circle, which is this. It would be nice if you even went beyond that and could look at it and say it was going to be this. Now, that's a luxury if you remember that that's the equation of a half circle, right? Because all that is solving this for y. So we take 64, subtract the x squared, do the square root, the plus is the top half, minus is the bottom half. And so there's our semicircle. And one side of the rectangle is on the diameter, so that's going to be down here. So what we have is this rectangle in here. That's the key. I mean, if you don't get this set up and get this equation, then you're just not going to be able to do the rest. Okay, but let's say you were to do that, or maybe I gave you this much or whatever. So what do I need to write down next? Area formula of a rectangle, which is length times width, right? All right. So what is this? What would I call this? Well, a more, I guess a better way to do is what would I call that point right there? X, Y, but we know Y is that, right? So that would be the smart thing, would be to do that right there. Okay? Yeah, so it's a little bit like Shanghai. We did that with Shanghai where we got a point we don't know what it is, so it's called XY, but we know what Y is, so it's that. Well, what that means is then, isn't this length right here X? So what's the length of my 2X? And what's the height? The height would be just the Y value, so that would be that right there. So there we go, right? If you remember what it was to do a maximum, it was identify what you're trying to maximize, write an equation for that quantity, get it in terms of one variable, which we have, and then what? We do the derivative, see where it's 0 or undefined. Okay, now here's where, this is a calculator one, right? So this is where the calculator really does come in handy. So get your calculators out. You've got a couple of options of where you could go here. Now, if I was doing this one, probably, and I was concerned about time and so forth, I think what I would do is just graph this equation. Now, I don't want you to, because we want to review the calculus, but what the heck, just graph it and see where its highest point is, right? And trace. I would say just graph this. Now, that's not using calculus, though, right? I'm just saying, on the AP test, on a multiple choice question, if you want the max possible area, set your window. What could X possibly be here? 0 to 8, right? 0, I mean, because this half just comes with it. So set your window 0 to 8 and just graph this area and see when it's at its highest point, right? But calculus would say do the derivative and set it equal to 0. Now, yes, you could graph the derivative. I don't think that's a bad thing to do. So go ahead and do the derivative, just for practice here. Go ahead and do the derivative of this equation. Make sure to put a time sign here in between that square root. I'm not sure it'll matter, but it's good to have it. But you do the derivative, and it's going to come out kind of a messy thing. Now, the downside to just graphing, I just thought of this. It just dawned on me. The downside of graphing and tracing to the highest point is you're going to get decimals, not these numbers. So then you would have to go in and check which decimal it was, right? Okay. But anyway, we do the derivative, set it equal to 0. Is there any place it's undefined? At 8. Oh, okay, well that makes sense, because at 8, that's just going to be a minimum. At 8, if X is 8, there's no rectangle, right? So there'd be no area. And that happened to us a lot on our area problems where the endpoints, that's kind of our endpoints, right? We can't forget about that. We have to check endpoints. The smallest X would be 0, well, there'd be no rectangle, so there'd be no area. And if X is 8, there'd be no rectangle, so there'd be no area. So a lot of times the endpoints were the opposite of what we wanted. They were the minimum, we were looking for the maximum. So endpoints, where it's undefined area, you have to worry about. So we solve it, what do you get? So you set that derivative equal to 0, do a solve, and what does it come out? Negative, which we can throw away, and 4 square root 2. Now, if you were tracing, you would have a decimal, and then you'd have to, right? Now, the danger here is you did all this work, you got your calculator out, you did all this, yeah, and then you circle that, and you'd be wrong. Because it says, what is the max possible area? So this is the X value. So you've got to take this and put it back into that guy right up there. And what's it come out? I think it comes out 64. What'd you do with geometry? I didn't think about it.
I didn't have it before class, but then right when you said you could have thought about it, and I just made the diagonals from the center point out to those points 8 each. And so then, like I made from the center point to that 8, so, and then I just did
because that's a radius.
Yeah, and then I did 2a squared equals 64, solve for a. So like a was my x.
But do we know that that would be an isosceles?
Well, if the way to make it, you know that the radius is what it's the radius.
Right, I understand that. But why'd you say 2a squared? Because I don't think this and this would be the same.
But if it was the maximum area of the rectangle, it'd be a square. So
This part would be a square. That could be, because together it's not a square.
Right.
But this piece would be a square. I think that could be, I think that would probably be good reason.
It came out as 64 because you got
Yeah.
like 2 root 32 times root 32.
Right. Yeah, and that's what I was talking about. I had a feeling anytime you're talking about circles and those kind of things without some other kind of thing playing in there, a lot of times there's kind of a geometric argument that can be made. So it's possible you could think through that. And again, on a multiple choice, you can get away with it. It's fine. I think sometimes you can spend more time finding that than just going through the calculus of it if you're comfortable with the calculus of it, especially when you've got a calculator that you can do with that. All right, good one. What else? 41. And I often have to, keep in mind that we can use our calculators here. Although I do think when I look at a problem like this reminds me of one that I could see being on the no calculator part now. Because of the CAS calculators that'll do more of this stuff, they've changed a little bit on that. So let's think about this without a calculator and see if we run into issues. So if you have this and they want to do that, it's kind of like working backwards, right? If we knew what f of x was and we asked for f ln x, we'd put ln x in. Okay, so anybody want to discuss their thinking on this one?
Also, I started out and said somehow the natural log of x equal x squared. So I put natural log of x equals x squared and just the square of both sides. But then that got me nowhere.
Right. Because it's not quite that natural log has to equal x squared, but when we plug natural log in to something, we get x squared.
Yeah.
So, anybody else?
I just plug that into all the answers.
Okay, that's one of the thoughts I had is it's got to be one of these, and it's doesn't take too long. I mean, because remember, e and natural log kind of cancel each other out, right? So if I put natural log into here, I get e and ln x, which would make, or e to the ln x, which is x, and you get square root of x. Well, that's no good. Here I do ln of ln x, well, that's nothing that I know of, so that's not going to work. Here, if I put ln x in here, yeah, and actually, as I'm starting to see my pattern, I'm starting to like this one here more and more all the time. But as I look at this would be e. Now, don't forget that's x to the 1/2, right? Now, if I put ln in there, did I do that right? Yeah. And what is this equal to? This is, remember, a power on a power is the same as multiplying the powers. So this would be, wait a minute. Whoops. I want to make sure, now I got to make sure I'm doing this. Hang on, let me get, well, I got to make sure. This is x to the 1/2. So this is e, where's the parentheses? The parentheses will be here, right? So, oh yeah, I had it right first. Okay. All right. So, start over. So this would be e, and now in place of the x, I'll put ln x to the 1/2. Okay. So this is that right there. Yeah, I don't know. I don't think so. Yeah, see, because I was thinking we could bring the power down in front, but you can't. It's not inside here. But there's no way it's going to be x squared. Okay? This one, the reason I like this one, I could tell I'm going to like this one because we're going to get this right here. Okay? And now, since this 2 is in front, I can move that inside. So this is e to the ln of x squared. E to the ln of x squared. Those two cancel each other out and just get x squared. See the difference here? Somebody type this in your calculator because it should simplify it. And make sure you get parentheses in the right place. Which can be tricky, as you notice the way I was struggling too. But I don't think because we don't have power on a power here. We have a power inside of power. Yeah, it doesn't simplify. Yeah, so that one we can't cancel the e and the ln. Here we just have ln of ln, which doesn't do anything good. So it ends up being this one. Okay, so I like what Josh said. I think you just try it. You just try it. Okay. All right. 45. Well, we can graph this on our calculator. We shouldn't really need to, though, quite honestly, right? It's a parabola. It's shifted 2 to the right and 2 up. And it didn't graph it right. That's weird. And then it's going to go down. See, your x is 1, 3.5. See, let's go. All right, so it's something like this, and so the idea is that the tangent, now b is the y-intercept, so it's going to be greater than or equal to 2. So it's got to be up above here, the y-intercept, which makes sense because any of the lines on this side, right, of the parabola, they're going to be, their tangent lines are going to be down here, right? We're talking about the tangent lines that are on this side of the parabola, right? They're going to have y-intercepts that are going to be greater than or equal to 2. But the question is, what are all the possible values of b? In other words, you could get one right here that's just a horizontal tangent line, right? And it would have a y-intercept of 2. And then as you go up and up, as you go farther down here, what's the... Oh, it's in the first quadrant. There we go. I was going to say, geez, I could go for infinity. But yeah, what we have to do is find where it intersects right here. Now, where is the y-intercept of this one? That's all we got to do. So we got to find out what this point is here. So where does that cross? Is it at 3, 0? Crosses at 3, 0. So you can do that by tracing, you do it by solving, set this equals 0, whatever. Graphing. So it crosses at 3. So basically we have to find the equation of the tangent line there, because we know there's going to be equation of the tangent line here that crosses at 2. mostly this is about the verbiage and the what's it asking, right? That's the hard part of this one. So the tangent line here is going to cross at 2, so that's a y-intercept of 2. And then all of these are going to cross up higher until finally you get to the last one in the first quadrant. And where's its y-intercept going to be? So the slope, so we do the derivative. Yeah, so the derivative, we bring the 2 down in front, which would be -4, leave the x minus 2 alone. To the first, the plus 2 will be gone, so there's f prime, so put a 3 in there. 3 minus 2 is 1, so that's -4. So our slope is -4. It's at the point 3, 0, to be that. So y equals -4x plus 12, right? So the tangent line here, so you're going to have a y-intercept of 2, and then they're going to go up, 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 up. You get to this last point, it's going to have a y-intercept of 12, so the slopes are going to be from 2 to 12. And the reason they didn't include 12 is because it's not technically in the first quadrant when you're on the axis here. So this one has a y-intercept of 12, so if you go up just a little bit to get in the first quadrant, then the y-intercepts will be less than 12. Okay? So that's just one of those, we kind of know all the things we need to do. We just don't know for sure what they're asking. It's just different ways of asking the questions. So we were not. Or 4 or 5. Did you do them?
I did A on 4.
Which parts you could? Yeah, don't worry about 3. Actually, I think I just said number 6. Early in the week, last week I said 6. And then I said 1 and 2 is kind of what I was interested in. But we will do them. So, yes, Ryan.
We do 43.
43. Yeah, I've still got at least one more multiple choice one I want to do that nobody's asked about yet. Let's look at 43. Okay, oh yeah, good. We haven't done one of these for a while. Piecewise functions, very, very common. They're usually 2 questions they ask. What will make them continuous, and what will make them differentiable? What do we have to do if they're going to be continuous? They have to have the same for continuous. I mean, forget what this is asking. Just they have to have the same y value, same output at the x value where they break. Right? If you have piecewise function, this one's coming in, this one's going out. It's only continuous if, right, they touch, right? This one comes in, and then this one goes out from the same place. Otherwise, there's a gap, and it wouldn't be continuous. So they have to have the same y value. Now, to be differentiable, it has to have the same slope, because you can't have one come in like this, and then the other one go out like that, because then the derivative doesn't exist because you have a sharp point. So the slope at this one coming in has to be the same as the slope at the one going out. So you add that component to it. Basically, if you know those 2 things, you can do about every piecewise function problem you ever run into on the AP test. Okay? So, since they want to know differentiable, they have to be both of those, right? It's got to be continuous, and then they have to have the same slope as well. All right, so put a 0 in for x into this one. E to the 0 is 1. 1 plus 2 is 3. Put a 0 into this one, you get b. All right, so we just figured out b. Okay? B has to be a 3. All right, now, to have the same slope, so we do the derivative. This one would be negative e to the negative x. And that has to be equal to this one, which is a. Now, and that's when x is 0. So we put a 0 in, we get e to the 0, which is 1, we get -1, we get a is -1. So, to be differentiable, b has to be 3, a has to be -1. Now, they ask it a little differently here. They said, what's a plus b? Well, a plus b is 2. So, a lot of times they just say find a or find b or find both or whatever.
Wait, so why does -e to -x have to be 1?
Because that's the slope of this one. I just did the derivative and the derivative of that. Because a is just a number. Yep, a is just a number, so the number in front of the x is the slope derivative. Okay? All right. What else? In the multiple choice. Nobody's hit on the one I was going to ask about. Maybe you got it worked out. I'm not telling you. Somebody got another one? No? We got time to do another one.
34.
Bingo. That's the one I was going to ask about.
It did it.
Now, hang on a second. Let me ask you a couple other ones. We won't do them necessarily. But what about 38? Now we're way back to 34 here. Let's look at 38. What's that?
Yeah, 38 we did. It's decreasing.
We did it? I don't think so.
I don't think.
Yeah, we did. I said A.
I don't think we did. I think you might have looked it up in the book or something in your groups or something, but I don't think we've talked about it. What is this?
That's the derivative.
That's the key. You got to now that's a form of the derivative we didn't use very often. Okay? As x approaches 3, because what this would be, we did the a plus h version of the derivative, right? Most of the time. But what this was a variation of that, but it was not one we used very much. But if I did a g graph here and I made this be 3 and made this be x, then this point would be g of 3, and this point up here would be g of x. And so the slope would be g of 3 minus g of x. If you subtract those and 3 minus x, that'd be the slope. And then as x approaches 3, the 2 points would become 1. So that is derivative. That is derivative. Okay? So what you're saying is g prime is negative. If g prime is negative, then g is decreasing, and that's it. Okay? But again, the idea is, it's not a hard concept, but what are they asking? Do you understand the terminology and what they're asking? That's the key. All right, let me see. I thought there was another one here. Yeah, this one right here. 37. Not a hard one necessarily, especially when you got your calculators. It's this messy looking function. But it says f is increasing most rapidly. When, okay, there's two ways to think of it. One is what Kelsey said. When f prime is a max. Increasing, which means its slope is the steepest. So that means when f prime's a max, where do you look? For f prime to be a max. F double prime is 0, right? So that's one way to think about it. The other thing to think about in a curve, at what point is it going up the steepest? And just look. Where is a graph going up the steepest? At the inflection point, right? That's when a graph is going up the steepest, the inflection point. Where do you look for an inflection point? When the second derivative is 0, right? Either way you think about it, it's going to involve where the second derivative is 0. Now, again, talk about little shortcuts you can use on your calculator. It would be okay in this one, acceptable. You could just graph f. There, we have a way on our calculators of finding the inflection point, right? If you go to the menu under calculus to inflection point, you can actually trace, because you do have to be careful. If you just do the second derivative and set it equal to 0, you could get when it's decreasing the most rapidly, right? You could get an inflection point where it's going down. So you could find a minimum of f prime. So that would be something you'd have to be careful of. Because I'm guessing if you do f double prime and set it equal to 0 and solve, you get a couple of these answers, would be my guess. I didn't do it, but my guess is you get a couple of them. Probably one when it's going up and one when it's going down. And you got to have the one when it's going up. Okay? But yes, you could graph f and just look at the inflection point. Kelsey, you said you graphed f prime and just looked when it was a max. That'd be fine. You know, again, if this was a free response, though, those would not be acceptable. You'd have to do the whole f double prime, do a number line, show that it's a max, that kind of thing, right? But for multiple choice, we could do that. All right, let's talk about 34, because that kind of leads me into something I want to talk about when it comes to the free response questions anyway. All right, now not everybody was asking about this one, so tell me what you did. Does somebody have a way they did it?
So I found the definite interval from 0 to 1.
Okay, stop right there. Holy cow. Good job. But I can see a lot of people look at that and say, where in the world did you ever come up with the idea of doing a definite interval? Now, maybe you remember because we have talked about this, but let's back up a second. Let's get everybody on the same page. Normally, if you read that f is an antiderivative of this, well, first of all, what can I label this?
Little,
Little.
F prime.
Wouldn't this be f prime? if little f is an antiderivative, then this would be f prime, right? Okay, and then they give me this, which is kind of like an initial condition, right? So what would be your normal thought process? And my guess is you guys probably thought this too at the
Oh,
beginning.
yeah.
Your normal thought process is to do what? Take the antiderivative, right? And then you're like, oh God, I don't know how to do that. And then you remember it's a calculator problem, so how about let the calculator do the antiderivative? Okay, try it. Many of you have not done this, I don't think. Do you remember how to do an antiderivative on your calculator? How do you do it? Do the integral without the a and the b on it, right? Okay, so if you try that, if you type this into your calculator with the integral symbol without the a and the b on it, asking the calculator to do the antiderivative, what happens? It's not actually a huge mess. It just gives it back to you. It doesn't give you anything. Which is a calculator's way of saying to you, I don't know how to do this antiderivative. Or it doesn't have an antiderivative. Okay? Now, we did this when we were doing the motion packet, because normally what would happen is you'd get the antiderivative, you'd tack on a plus c, right? That'd be your little f, and then what? Put your initial condition in, find your c, so that would give you your f function, then you put in a 0 and away you go. You'd have it. That's what we would normally do. Now, I would like for you, from this point forward, to move away from that line of thinking. Still okay. But as we learned, matter of fact, that's the whole point of chapter 6, what happens with some functions? You can't get an antiderivative. So that's where the definite integral comes into play. And I want to show you another example of this. But if you do, and this is fundamental theorem part 2. Fundamental theorem part 2 says that if you do the antiderivative of f prime, or excuse me, the definite integral of f prime, you get right? I want you to start thinking when you have an antiderivative type situation involved, when you have a f prime function, a rate function, I want you to start thinking in terms of integrals, definite integrals. Because here's the beauty of definite integrals. We just learned it in chapter 6. If there's no antiderivative, can we do the definite integral? How? By an approximation. And you calculate, just like what we just got done doing the quiz on, the K1 and the K2 values, right? The calculator cranks out how many subdivisions do I need to get within 12 decimal places of accuracy. The calculator can handle definite integrals even when it can't do an antiderivative. That's when we want to do this. So, in this problem, we're going to take that function right there, whatever that is. 0 and 1 are really good choices because what that's going to give you is f of 1 minus f of 0. Now we can do this on our calculator. I think it comes out 0.3446 something. Over here we know f of 1 is a half, which would be 0.5. And we don't know f of 0, and so therefore we can solve for it. So I just add the f of 0 over to the other side, subtract the 0.3446, so it would be 0.5 minus 0.3446, which must be b, must be that one right there. Okay, now, oh, I am recording, so I probably better not do that over on the board over there. So let me do this. Okay, so again, let's repeat this. So we have an f prime. They were asking us about f. Normally we would say do the antiderivative, which is fine. If you can do the antiderivative, go for it. But often you can't. That's okay. Definite integrals we can do even if we can't do the antiderivative. So if I look at a problem like this is where I first told you guys about this. It had to do with velocity. Now let's say I gave you a velocity. Let's say this was meters per second. Let's do an easy. And I wanted to know something about this particle. Let's say it had a starting position of 1. And I wanted you to tell me where this particle was at 2 seconds. Okay, so the particle moving back and forth on the x-axis. Here's its velocity. Here's where it started. You tell me where it ended. Is this not the same problem? Isn't it pretty much the same thing? Because this right here is x prime. Now, the difference is, yeah, can we find the x equation on this one? Sure. Antiderivative, what would it be? 3/2 t squared plus 2t plus c. That would be the position function for this. And you might run into a problem where they ask for the position function. So yeah, you'd want to be able to do this. Then we would put our initial condition in. C would be a 1. So 3/2 t squared plus 2t plus 1. And so therefore x of 2, 4 times 3/2, that'd be 6. Plus 4 is 10. Plus 1 is 11. So this particle started at 1 on the x-axis and ended at 11. Now it may have turned around at some point in there, but that's what it did. Now, let's look at that from a definite integral perspective. Couldn't we have done the same thing? We could have done the integral from 0 to 2 of 3t plus 2 now, yeah, but now the question is, what would you have done with this information? Would you have done fundamental theorem part 2? Would you have said, okay, this is x prime, so this is x of 2 minus x of 0? Would you have done that? Maybe, and then you could have done your antiderivative, but that would have been the same, right? So you just said, okay, I don't know what this is, but I know this is 1, right? And then you do this, say, do this on your calculator, let's say. And that comes out to be, must come out to be 10. So that comes out to be 10. And then this would be x of, did I do that right? Or did that come out 11?
No, 12,
2 squared is 4. That'd be 6. 2 times 2 is 4. 6 plus 4 is 10. Yeah, okay. So if we do this integral, anybody do it on their calculator? It's 10, okay. And then this is something we don't know. And then, so we add 1, and sure enough, we get that. But now, if we had it on our calculators, whatever. So, actually,
just do, have a 2, 3, 2, 2,
yeah, right. In other words, I could have basically done the same as this. Done the antiderivative, done the right bracket, all that good stuff. Okay, but here's the other thing I want to leave you with. What if you just would have set up this integral? This is the part I wanted to really get across here today. What if you wouldn't have done this whole fundamental theorem part 2 thing here? What if you'd have just got out your calculator and done that?
you get 10, and then you have to go,
Okay, there's the thing we started talking about before break. A definite integral of a rate of change is the amount of change. In this case, net distance traveled. Remember that discussion we had? Net distance traveled. So if you looked at this and said, oh, hey, this is velocity, meters per second, I'll just do the integral of that, and that'll tell me how far I traveled. And so you do the integral and you get 10, but that's not the answer because you started at 1. So you have to take that into account. So what this says is how much you traveled from 0 to 2. You went 10, but we started at 1, so therefore I ended at 11. So you could get the answer that way. So I really want you to see the various ways we can attack this problem. Again, when you do an easy one where you could do the antiderivative, you've got a lot of options. But if we go back to this one that we did in the packet, not nearly the number of options. You pretty much just had to do it this way. Okay? All right. And the difference here is they don't give you the starting point either. Here you could have just done this integral and then said, oh, but you started at half. But that's actually where you ended, wasn't it? That's where you ended. What they wanted to know is where you started. So you could have just done the integral. Instead of setting this whole thing up, you could have just done the integral and said, oh, that's 0.3446. You could have thought, or no, 344, I said it right, I just wrote it. So 0.3446, you could have done that integral and said, okay, if this is like a velocity, then this is how far I traveled. This is where I ended. So where did I start? Right? So you do 0.5, take away that, would tell you where you start. So you could have thought it through that way without writing it out like that as well. Okay. So that's a pretty good way to get to those. So we're going to see more of those, and hopefully that'll become easier and easier for us as we go. All right. Let's go to the free response. Let's go to number 2 first. All right. This is a very, very common problem in the free response. 6 free response questions. Almost always one of them has to do with some rate. It could be the rate that something's cooling. We've seen that. There was one a few years ago with people waiting in line at a concert, and then they opened the doors. And so before the doors opened, the number of people in line was growing by a certain amount per hour. It was the rate. Then once they opened the doors, now you still had people coming to get in line, but now people were going in too, right? So they wanted to know how many people were in line at a certain time. Does that make sense? See how that's kind of the same as this? You got sand going into the tank, and then at a certain point they open the plug, and now sand's coming out. So you got sand coming in and sand going out, and what's going on with the sand. Okay? So it's a very similar type of situation. Now it's important to know that S and R are both rates here. Okay? So once you get over that hump of what this is and you recognize that this is the same kind of problem that you see over and over again, it's really not too bad. So how much sand is put in the bin during the workday? Of S. And on the actual AP test, this would be fine for your work, and then just put your answer down, because this is cubic meters per hour, so the integral would be cubic meters, or another way to think about it is the dt is like hours, so cubic meters per hour times hours is cubic meters, and that's the sand going in, and it doesn't matter what there was to start with, because only one is how much sand is put in. They're not saying how much is in the bin, right? Are those two the same? Unless it starts empty, which actually this one does. So since a tank starts empty, how much goes in is the same as how much is there. That is until they start draining it out. That's true. But yeah, okay. So on this one, they had 415.421 or something like that. All right. Now, find S of 6 minus R of 6. Well, that's pretty easy. All you have to do is plug those in and subtract. And it comes out to be negative 39.910. And that would be cubic meters per hour. What does this mean in the context? So the sand volume is actually going down by that much per hour. So obviously at 6 hours, it'd be important to put that in. At 6 hours, the sand volume is decreasing by that rate, at that rate, okay? So it's coming out faster than it's going in at 6 hours. Why is the max amount of sand in the bin when S is equal to R?
After that, R is greater than S, so sand's getting faster than it's being put in.
I like, yes, exactly. Basically, you have 3 possibilities, right? Either the sand is going in faster than it's coming out. In that case, the sand volume is increasing. Or the sand rate is less than what's coming out, then the volume is decreasing. And when they're equal is when those are balanced out. So in the beginning, this S is greater than R. So the sand volume is rising, then when S equals R, it stops, and then after that, like you said, it starts falling. So some kind of discussion about that is what you'd be looking for.
So can you just talk about that, or do you have to like bring in like S prime or R prime?
Probably, let me see what they did here. Now, although just because the way they graded it here doesn't mean that's how the EP would. They actually did this. They had 2 ways. Well, actually, I like one of their explanations. I'm gonna show you that. But one of their explanations was this: before the time when S is equal to R, the rate at which the sand is being poured in is greater than the rate it's taken out. After the point where S equals R, the rate it's taken out is greater than the rate it's going in. So that's like what I was just telling you. So therefore the max is when S equals R. So that would be acceptable, I think. Now, they did do something, as another one of their explanations, which I kind of like because I've seen this on AP test questions before. So let me rephrase that question. What if they just said, write an equation involving an integral, I'm sorry, not an equation, an expression. Write an expression involving an integral that will give the amount of sand in the bin at any time t. Write an expression involving integrals that will give the amount of sand in the bin at any time t. Well, we're getting close. Actually, I've got several things wrong. That can't be t. Yeah. Let's just use R and S for right now. And then this one would be from 0. Well, if I use t here, then I'd put t here. And this would be from, right? Now, then I couldn't use t down here, right? So I'd have to have something else, right? So actually you could just leave it R and S, probably be fine. Okay, what you wouldn't want to do is have t's there. So let's say we use x's. Okay, whatever we have in here doesn't matter, just can't be t. This, and I've seen this on the AP test. I've seen this as one of the questions. Write an expression. No, it's not. It's dx, yes. Write an expression involving integrals that gives the amount of sand in the bin at any time t, because this is the amount we said that went in minus the amount that went out at a certain time. Now, where will this amount be a max? Well, no. Yeah, forget all this. Yeah, when is big A a max? When A prime is 0, right? Or undefined, but we won't get into that for this one. That's right. That's fundamental theorem part 1. What's A prime of this? S of t. The x turns to a t, remember that? And does the 0 matter? That's just the plus c part. Okay, minus r of t. And it's going to be when that is 0. So that's when s of t equals r of t. So they give that as another explanation of how you could say that is. But I did like that exercise right there of just doing this, because I have seen that in problems where they say, write an expression involving integrals. And then, in this case, for the amount of sand in there at any time t. Okay? And so that means you just have a t. All right. So, good stuff. Let's go to, let's see, are we done with that one, or no? We had more. How much sand is in the bin at the end of the day? So we would do the integral from 0 to 9 minus the integral from 1 to 9, which, well, of course, that would fit in nicely with what we just wrote up there, right? I mean, that's basically how much is in there at 9, right? It's how much went in minus how much went out. And it comes out negative, which means it's empty, right? It's empty. They're basically about the same. But it did come out a little negative, which means there wouldn't have been anything left. Can't have a negative amount of sand. So it's empty. Okay? All right, that's number 2. Let's go to number 1. and this is pretty good review, even though some of what we just talked about does fit in here. So this is a calculator one, so they give you the velocity, so we were already talking about that a little bit earlier. Find the velocity at 3, so that's easy, V of 3, and they give you an answer there. I don't know what you guys, negative 0.841 or 842. And then what's the speed? The what? No. It's the positive value of that, right? So it'd be 0.841 positive. And then the acceleration, that's v prime. So you do the derivative and plug in a 3. Yeah. Yeah. Did you come out with like something? Yes, that is acceptable. That is acceptable. And I think that's a good idea. If I'm taking the AP test, I'm probably leaving it like that. Yeah, so I don't mess up the decimals. But yeah, decimals are okay. The book here happens to put decimals, so 3.906 they got for this last one. You do the derivative, plug in your 3. All right. Now this is interesting. In the viewing window, now sometimes they do this. So sketch the graph of V. Well, that's easy, right? You just got to type it in your calculator. Set a window, do a zoom fit maybe. It kind of goes up like so, levels off, and then comes up, kind of like an x cubed curve a little bit. At least that's what they've got drawn in here. Kind of an x cubed, kind of flattens out there. Now this is an interesting question here. It wouldn't be a bad idea. Because they do come out to be 1, I think, don't they? Or no? So they don't quite hit in the corner. They don't quite hit in the corner. That's actually, I can see that now in their graph. So they don't quite hit in the corner. Okay, they're up here. So mine's off here. So you would want to sketch that pretty carefully, right? I mean, if you were doing this on the EP. Now, is the velocity increasing or decreasing? This is the velocity. Increasing. Use your graph to justify. Yes, I mean, I'm reading in the book. Here's what they say. Its graph is raising throughout the interval. I don't know. Would it be rising? Would it be its graph is rising? Raising? Now, I mean, I'm reading that. I thought that would be a confusing one because you think there's no way. This is way too easy. They must want something else.
Yeah.
I think what they're getting at is they want to see if people would be confused by where it flattens. Is it still increasing the whole time? And the answer is yes. It just like x cubed. Even though it's got a 0 slope at that one point, it does flatten at that one point. It's still increasing. The points are still getting bigger as you go from left to right. So I think that was kind of the gist of that question. All right, but here's the one I really wanted to talk about as it relates to everything we were just talking about with integrals and distance and all that stuff. Find the distance the particle traveled from 3 to 5. Definite integral from 3 to 5 of what? The V graph? No.
No, it's a speed.
If you type that into your calculator, you're going to get 0.
Oh, yeah.
You see what I mean? If you just do this, now you probably catch it because if you just do that and you type it in, you get 0. You're like, oh, it didn't go anywhere. Well, then you start looking at the graph and you say, oh yeah, the area that'd be this, and then this. Well, those are going to cancel each other out. So what's happening? Now this is a particle on the y-axis, so what it means is we got a negative velocity early, then a positive velocity. So it went down, then it went up. And it ended up right where it started. But that's not what they wanted. So yeah, you really need bars around that right there. Now you also could have said, well, because of symmetry, you could have done the integral from 4 to 5 and doubled it. You could have said that, or whatever. But yeah, this whole thing, and hopefully this kind of reminded you of it up here when they talked about speed. So what is like 0.293 or something was the distance traveled. So you have to have bars around it. That's total distance traveled. Now they don't always use the word total. Sometimes you just say the distance it traveled, that's the same as total distance traveled. The net distance traveled, or the change in distance, would have been the other. So we do have to keep those separate. All right, I'm going to let you work then. I'll give you a little bit of a hint since it sounds like some of you went on to that anyway. So basically we're going to skip 3 for right now. We'll see if we have some time later in the week. I'll talk about it. At some point I will talk about 3. There's part B we can't do yet anyway. And it's the last new thing we'll learn. So last part of chapter 7. And so this gets into some tricky, and it's kind of confusing with this. So we'll just leave that one for right now. But 4, let me talk about 4 real quick. 5 should be the easiest of the bunch probably. On 4, what's it look like? Doesn't it look like Shanghai? It's actually easier than Shanghai because there's 2 graphs. Okay, again, what's Shanghai about? Shanghai is about, we have, the whole point of Shanghai is we've got some curve with a tangent line touching it. We don't know where it's touching, but we know some other point over here. So the way we do Shanghai is we have 2 slopes that are equal to each other. We have the derivative, which is, right, and then we have the slope between the 2 points. And we can set those equal to each other. But this is easier than that. This is easier than that because this point right here, we can do the derivative to get that slope. So we can do the derivative of that function and plug in an a. And then this point, we can also do the derivative because we have a graph for it too. So we don't need to do slope between 2 points, at least for part A anyway. You might need to on part B. So you got this, and now you can do the derivative of this equation, plug in a b, and that's the slope of that point. But what do you know about the slope here and the slope here? They're equal because they're on this same line. So they're equal. So now you can do that, and then that should take care of part A for you. Then part B you might need to do, but once you do part A, then you can do a substitution into one of these points, and you can do a slope between the 2 points kind of calculation. That should help you get part B. Once you know that, then part C, write the equation of line's easy because then you know what those points are, and then you can go from there. Okay, and then 5 is a little more of just a typical number line, max, min, increasing, decreasing. Okay, all right. So I'm going to give you the rest of the time to work on those, and then any others in the packets you need to get caught up with. And tomorrow we will start with chapter 7. So that's your only assignment. Uh-huh. Yes.
for slope between 2 points, but what do you set that equal to?
Well,
Because like I was trying to plug that in.
well,
there.
whatever, that or that, because that's slope. If you do slope between 2
Oh,
points,
okay.
then both of those are that slope. So you can set them equal to either.
So you could either do like a plus 3 and put that in for b, or you could do.
B master and put that in for either way. Yep.